Inside this box, I have an egg and the box is completely closed, so I also have an LED inside so you can see what's going on. As I film with the GoPro, I have taped inside the box. I'm gonna do something to the box. Watch closely what happens. Can you guess what I did? Hey everyone, I'm Dianna, and welcome to lesson 5 of Dianna's Intro Physics class, also known as AP Physics 1 Review, also known as Physics by Dianna. Today's lesson, free body diagrams. That's the new tool we're gonna introduce today. And my friends, buckle up, because free body diagrams are gonna allow us to measure G, the acceleration from gravity on Earth, that gorgeous, delicious 9.81 meters per second squared. We're gonna measure it. Here's a teaser on how we're gonna measure G. I have strapped myself into a death-defying contraption. It's called an Atwood machine. Once I trigger the release, this machine is designed to let me fall, but very slowly. This is gonna allow us to measure the acceleration of gravity near Earth's surface precisely, which is really cool. So today's theme, gravitational field trip. It's funny because we're taking a trip in a gravitational field. Gravitational field trip, do you get it? So we wanna measure gravity. What is gravity? It's a force. It's actually called a fundamental force. I wanna go off on a fun little tangent. That one was not my fault. Gravity is actually called a fundamental force. Are there other forces besides gravity? Yes. There are 3 more. I know you know one of them. It's the electromagnetic force. It's the one that makes magnets stick together or push apart. Yeah, there's little magnets in here. Stick together. And strangely, the electromagnetic force is the same force that makes balloons stick to your hair with static electricity. And there are 2 more forces. The weak nuclear force, no one remembers that one, and the strong nuclear force. And you can Google them. That's it. These are the 4 fundamental forces. There might be more. We don't have any evidence for them, but our known laws of physics don't rule them out. So, is gravity the strongest force? Check it out. I can use a magnet the size of a pea, it's smaller than the size of a pea in here, to pick up a nail. So this tiny little thing can overcome an entire Earth's worth of gravity. Proportional to mass, gravity is actually a really, really weak force. There's just a lot of it. But puny as it is, it's still pretty important, and that's the force that we're measuring today. Up until now, we've just accepted that things falling near the Earth accelerate at 9.81 meters per second squared, which I usually round to 10. But we're gonna confirm that number with our experiment on the Atwood machine soon. But first, we're gonna need a new mathematical modeling tool. Get rid of this stuff. It's called the free body diagram. A free body diagram is a simple picture that represents all of the forces acting on an object, like a cow. It's kind of a funny phrase, free body diagram. But the word body is a physics term for object, and it's free, which doesn't mean it's free like a bird in the sky. Free means we're looking at the cow alone. It may be connected to other cows, experiencing forces from the other cows, but we're isolating it, and we're drawing only the forces on that cow. Not physically, but with our math. So, how do you make a free body diagram? Let's draw one for a falling bottle of nail polish. I dropped a bottle of black nail polish on the floor once. It was bad. We're gonna ignore air resistance for now, and we're gonna ignore these cows. So for a body falling near the Earth, like nail polish, gravity is the only force. But I'm gonna model it as like a point particle, because we do that. So that's F sub G. I'm gonna represent that on my diagram with this arrow to remind me that it's a vector with a direction. And we know that the force is mass times G. That's it. That's my free body diagram. It's not complicated. We can make free body diagrams for projectile motion problems too, from lesson 3. So neglecting air resistance, here's a soccer ball flying on its parabolic path right here. How would I draw the free body diagram? Gravity is causing a force downward. Here's my soccer ball. I'm drawing it isolated. Here's my force of gravity, F sub G. Are there other forces? You might be tempted to draw a push from the kicker, but no, I say, don't do that. When the soccer ball player's foot is in contact with the ball, there's a huge force accelerating it, but we're drawing the ball after it has left the foot, which means that force is gone. So neglecting air resistance, the free body diagram of an object in projectile motion looks like this. Look familiar? It looks just like the free body diagram of an object falling straight down, which makes perfect sense because you remember when we looked at projectile motion, the key idea was to separate out left and right motion from up and down. And in projectile motion, there are no forces acting left and right. So the only force is down. So the free body diagram of a cow falling and a cow launched in projectile motion are the same. A lot of people get that wrong. So we've been neglecting air resistance for now, but let's think about it for a hot second. In physics, it's good to consider what you're ignoring before you ignore it, and if it's a good reason to ignore it. Air resistance is a force created by air pushing against a moving object. So when you stick your hand out of a moving window, for instance, that is air resistance. It's not wind, because you feel it even if the wind is not blowing. And when the car stops, you stop feeling air resistance. Air resistance clearly changes depending on your speed, and it always works against your motion. You can start to tease out this relationship with speed when you think about how air resistance slows down a skydiver in a parachute to land softly. Let's make it David Blaine. Let's draw his free body diagram. This is the best stick figure I've drawn so far. There's gravity downward proportional to his mass, Fg equals mg. And what about the force of air resistance? At the top of the flight, he's not moving. Just like in the stopped car, he isn't feeling any air resistance. But as he falls faster, the air resistance increases, and it's going to be the opposite of his downward motion. So it's going to be like this, F of air. But it can't be too big, or else the sum of the forces, like if it was up here, would be up and he would shoot out of the atmosphere, which would mean that David Blaine would eventually bounce off the air and land on the moon, which I wouldn't put past him. That's clearly not what happens when you're skydiving. So the force of air resistance must eventually hit a limit where it balances the force of gravity down. So these should be equal in length. So the sum of the forces, which are equal and opposite, sum of the forces, F air minus Fg are 0. And actually, I'm gonna make this plus because we're summing the forces. So how these are gonna cancel out to be 0 is that this is gonna be negative. Either we could have written a minus in front of here, or we could say that G is negative. You always want one of them to be positive, one of them to be negative. That's important to keep track of. So just to be clear, he's still moving. He's just not accelerating. He's falling at a constant velocity known as terminal velocity. Here's a cool weird thing the air does. It curves the path of balls that are rotating. It's called the Magnus effect, which is when the trajectory of a spinning object, a spinning spherical object, curves because of air pushing on it. It's why you can bend a soccer ball when you put some spin on it. And if it's really smooth, it bends the opposite way. Crazy. But for the most part, we're gonna ignore air resistance though, because it's complicated. If you want more of a taste, the equations look something like this. Okay, no more tricky fluid dynamics for now. Let's take a look at the egg in the box. Did you figure out what I did? Check it out. I can make the weight on a scale go up, or I can make it go down by seemingly doing nothing. It's magic, or just sufficiently advanced physics. How is it that when I drop the scale a bit, the weight goes down and then up and then goes back to normal? Let's take a look. Let's scale it up. Let's think about a person weighing themselves on a scale, seeing how swole she's gotten. Let's draw her free body diagram. So what we're gonna do here is we're gonna look at the free body diagrams of a person on a scale when she's just standing there, and then when she's moving in an elevator at a constant velocity, and then when she's accelerating, and see how they differ. So let's start with the first one, where she's not moving. So what are the forces on her? There's the force downward from gravity, but she's not accelerating, so the scale on the floor must be pushing back on her. So that's upwards, my scale force. And these two forces must be equal and opposite. So my magnitudes are equal. And of course, Newton's third law, if the scale is pushing up on her, then she is pushing down on the scale. There are little springs in the scale getting compressed by that force, and then the dial, or the numbers, which is connected to those springs, shows the reading of that force. It's measuring the weight pressing down on the scale. Here's an interesting story. When we did the 0G plane, I know I talk about it all the time, they actually simulate Earth and Mars gravity by doing specific types of parabolas. And you can feel what it feels like to be on Mars or on Earth, and you fall a whole lot slower. That's true. They actually do that. So the scale is measuring your weight, but technically speaking, the scale measures the force compressing the springs, which means you can fool the scale about an object's true weight. So we're a little closer to seeing what I did with the eggs. Let's put our weightlifter on the scale on the Taipei 101 in Taiwan, which is the 509.2 meter high tower and the second tallest building in the world. The tallest building gets too much attention. The elevator is being pulled up by a big cable at a constant speed. So does the scale say that she weighs more? Free body diagram. What are the forces on her? So here she is in the box. Because we're free bodying her, we're isolating her. So there's gravity down, Fg, which is the same, mg. And then the elevator floor also pushes up on the scale, and the scale pushes up on her. But, and this is the key idea, she's moving at a constant speed. So the acceleration is 0. Which means F equals ma, my a is 0, so then the sum of my forces is 0. Which means that the force that she is exerting on the scale is exactly the same as when she was standing on the scale in the gym. It's weird, but it's true. But say that I'm in the elevator and it starts to accelerate upward at 2 meters per second squared from stopped. What will the scale read now? Free body diagram. Gravity is the same, Ft, but now we have some numbers. It's mass times g, so 58 kilograms times 10 meters per second squared. So my Fg equals 580 newtons. There's still the force from the floor keeping me from falling through the floor. So that's Fs, because actually from the scale, which is the same as the 580 newtons, but there's this extra little force from the elevator accelerating me upwards. So the sum of my forces equals Ma, which equals my Fs plus Fg. My mass is 50 kilograms. My acceleration is 2 meters per second squared, which I gave you at the beginning, and that equals Fs minus my Fg, 580 newtons. 58 times 2 is 116, so 116 newtons equals Fs minus 580 newtons. So Fs equals then 116 newtons plus 580. Fs equals 696 newtons. Beautiful. But without acceleration, the scale would have read 580 newtons. And Newton's third law tells us that I'm pushing back on the scale with the same little extra force. So I'm pushing back on the scale with 696 newtons. Another way to think about this is that the spring in the scale is being compressed up into me more, so the dial says that I gained more weight. Because if I weren't accelerating, the scale would just read this same Fg, 580 newtons. Now, I don't actually become more massive. The force of gravity hasn't changed, but the scale reads more. And I feel like I weighed more because the elevator is pushing me up. Crazy stuff. And I know I talk about this way too much, but a few years ago I experienced this concept in the most awesome way on the Vomit Comet, the 0G plane in France, which is that as the plane ascends, it's just like an elevator accelerating upwards, and I felt 2 Gs. And you can see my face drooping like I weigh twice as much. I was then advised to lie down because at 58 kilograms, I felt like I suddenly weighed 106 kilograms. I did stand up in the later parts of the flight, and it was a workout just to stay upright. So what happens if the elevator starts to slow down at the top of the tower? It's decelerating, so the sum of my forces must be pointing down now. The net force is downward. Because the force of gravity is unchanged, the springs in the scale must be pushing up a bit less. So the dial or the numbers on the scale go down a little bit, which means that if you control the acceleration of the elevator, you can change what the scale reads. You could put a set of brakes on the side of the elevator and tune them to slow down gradually so that you ever so slightly lift off the scale and experience a brief moment of weightlessness. That's what happens in the 0G plane. Your perceived weight on the scale goes to 0. You brake super fast and slam into the ceiling, so make sure you wear your helmet in an elevator. We should have gotten some padding for the eggs. Now we have our tools and we're ready to measure G with the Atwood machine. What is the Atwood machine? It came from this English mathematician named George Atwood, who invented the contraption in 1784 to study constant acceleration. So it's basically this machine on a pulley with a rope. Here's my pulley with a rope. And 2 masses on either side. And one mass is a little bit heavier than the other side. So M1 bigger than M2. By the way, you can see that in the Atwood machine we made, we have 2 pulleys, so we could keep the person separated from the weight so they don't smack each other. So I'm here with Thea. Behind us is the human-sized Atwood machine. Thea made this. Do you remember like what the specifications were?
So the specifications for this were basically it had to be human size, support Dianna safely, and be as frictionless as possible because it's a pulley system. We're offsetting 2 weights and we want to make sure to minimize variables.
Okay, so these masses will accelerate, but slowly, because they're very close. And by timing the rate of the fall, we can use our free body diagrams and we can figure out G. Now you might think, why go to all the trouble of very slowly risking Diana's life on an Atwood machine? Couldn't you just measure gravity by dropping something? Well, even from these heights, things fall too fast. Let's measure it. I'm gonna drop this hair clip. We've measured out 1 meter, and I'm gonna time it. Here we go. I'm hoping to get 9.81 meters per second squared. Let's see. Okay. Ready? 3, 2, 1, start. Okay, I got 0.55 seconds. That gives us about 6.6 meters per second squared. That's a pretty big error from 9.8. My timing is terrible, and air resistance once again makes things difficult and messy. So by slowing everything down, I can measure more precisely. That's the point of the Atwood machine. So the motion of the Atwood machine involves 2 fundamental ideas. One is that the 2 masses are connected by a rope, which means that they will accelerate the same amount. Here, M1 accelerates down, while M2 accelerates up, but at the same exact rate. Key idea number 2 has to do with the tension in the rope. That tension pulls M2 up, and because the rope isn't stretching or compressing, it pulls M1 with the same magnitude of tension. Those are the 2 key ideas. 1, M1 and M2 accelerate at the same magnitude, and 2, the magnitude of the rope's tension on each of them are equal. I'm gonna just tell you up front that we're gonna neglect the mass of the rope. We're also neglecting the energy used to accelerate the pulley and the friction in the pulley, and we're being negligent to keep this experiment simple. So our procedure to find the acceleration is straightforward. We draw a free body diagram for each mass. So let's do it. M1, gravity pulls on M1. Let's put M1 here. At a magnitude of M1 times G. Tension is pulling it up, that's T. And there's no other forces. So the sum of the forces equals M1 times A equals T up and mg down, M1g, so minus M1g. But hold on, let me remind you to pay attention to negative signs. They're going to matter here. Down is negative, up is positive. So M1 is accelerating down, so I put a negative sign here in front of M1. That's it. We're gonna save this for later. Okay, let's do the procedure for M2. Mass 2 experiences the force of gravity down and the tension up. So T up and Fg is M2g. The sum of the forces on M2 is M2 times A, which equals T minus M2G for my gravitational force. And remember, M2 is accelerating up, which is positive, so no negative sign in front of M2 over here. So now we've done all of the heavy lifting, and all we have left is algebra. I have 2 equations here, what looks like a bunch of unknowns, but I can make it simpler by using my 2 key ideas. First, I remember that the tension, T, is the same for both ends of the rope. So I just solve for T, and I set my 2 equations equal to each other. So let's do it. T equals minus M1A plus M1G, and T in my second equation equals M2A plus M2G. So I just solve and set my 2 equations equal to each other. Okay, so minus M1A plus M1G equals M2A plus M2G. So I remember that the accelerations of each are the same, so the A's on each side are the same A, so I can combine those somehow. I'm gonna do that by moving these on the same side. M1G over here, minus M2G equals M2A plus M2A. Then I pull out the G times M1 minus M2 equals A, M2 plus M1. Okay, then we solve for G because we want to measure G, so we solve for G. G equals A times M2 plus M1 over M1 minus M2. So we get that. G is the acceleration I measure times the sum of M1 plus M2 over the difference of M1 minus M2. So now we just have to measure the acceleration, and we can measure G. So the T we got was approximately 2.15 seconds. The distance was about 2 meters. M1 was about 79 kilograms, and M2 was 65 kilograms. So plugging this all in, G equals, well, first we have to D equals 1/2 AT squared. So D is 2 meters equals 1/2 times A times 2.15 seconds squared. If we solve for A, we get 0.87 meters per second squared. So we're gonna plug that in then, 0.87 meters per second squared. And then we do M1 plus M2, 79 kilograms plus 65 kilograms over 79 kilograms minus 65 kilograms. And we get G equals 8.9 meters per second squared, which is not quite right. The real G is G equals 9.81 meters per second squared. But the thing is, there were so many places for margins of error. One is friction in the pulleys, which messes with our time, and that error gets squared over here when we do this calculation. There's also the masses. If we used instead M1 equals 78 kilograms, and we use M2 equals 65.4 kilograms, then we actually do get G equals 9.8 meters per second squared. So that shows you how sensitive this is to the masses. We also could have slowed it down. We could have made these masses closer together, but what happened then is we got more friction in the pulleys when they were moving slower. So then there's even more error. When we did that, we actually got a value of G equals 2. So we sped it up to get rid of friction, and then we had we needed more sensitive measurements on our mass, and and we were sensitive to within about a kilogram. So this is within the margin of error of our masses. Plus, the cable itself weighed about 2 kilograms, and that changes over the course of the movement. Lots and lots of error. But I say we did pretty good. Yay! We measured G. That's G at this particular elevation though. We were pretty close to sea level in Los Angeles. Remember, gravity weakens as you move further away from the center of the Earth. Gravity is less at the top of a mountain. If you were standing over a giant uranium mine, because uranium is a very dense metal, you would measure a higher G. G over the surface of the Earth varies between 9.76 to 9.83 meters per second squared. It's not always 9.81. Here's a map NASA made of the gravity anomalies around the planet that shows you will measure different G's depending on your location. I'm gonna show you one last extra trick for solving Atwood Machine type problems because they show up on exams super often. So a problem might give you 2 masses and then ask you what the acceleration is. So we need to arrange the algebra to look like this. Solving for acceleration equals G times m1 minus m2 over m1 plus m2. So the algebra looks like this. That's why the masses accelerate slower than free fall. So what I mean is, let's try it in a situation where m1 is twice m2. So m1 equals twice m2. So then my equation works out to a equals g. M1 is twice M2, so 2M2 minus M2 over 2M2 plus M2, which equals, this is M2 over 3M2 times G. So the acceleration equals 1/3 times G. And I get A equals 1/3 G, so it does work. You can use this trick for any combination of masses. The number of G's you measure is the difference of those 2 masses over the sum. Gravity only gets to work on the difference of the masses, but it's the sum of the masses that get accelerated. It's like gravity has to accelerate 3 masses, but only gets to work on the equivalent of 1 mass. We're used to everything falling at the same rate because gravitational mass is equal to inertial mass, but in the Atwood machine, that lets us fake out gravity. So that's lesson 5, how to use free body diagrams to calculate forces. Okay, so that's lesson 5. When they ask you what you learned on YouTube today, here are your 2 important takeaways. When solving problems using a net force, FBD, free body diagrams. When solving problems with multiple components, look for variables they have in common. And as always, you must solve the problems. It's the only way to truly, really learn physics. So here are all the problems we did today for you to rework on your own. And you can also search on the internet for free body diagram problems and gravitational acceleration problems for more practice. You should. And now, a message from a very special guest, Bill Nye.
Greetings, Bill Nye here. You know the old saying, everything happens for a reason. Well, that reason is usually physics. Physics is the fundamental science. So enjoy this course. You can't do any better than Professor Cowern, and then get out there and make things happen.